Welcome to our webinar, Optimization and Design of Turbo Machines using ANSYS optiSLang and CFturbo. Presenters for today will be Maes Kufanti from CFturbo and me, Markus Wagner from Danado. So let's have a look at the agenda for today. We'd like to give you a small introduction into optiSLang and CFturbo, and then have a look into two case studies, optimization of an actual pump, and the performance map analysis of a radial turbo compressor. Both analyses will have the same structure. We will have a look at the aim of the analysis, the CAE workflow, how it is set up, this automated process chain. We'll have a look at the results of the variation analysis, of the sensitivity analysis, the optimization, and have a look at the summary. So now let's directly start with the introduction into Danado and optiSLang. Danado was founded in 2001 and has now more than 60 employees. Had two offices in Weimar and in Vienna. So here you can see the office in Weimar, and it supports leading technologies, companies with leading technologies like Daimler, Bosch, Siemens, and so on. Danado is split into two parts: CAE consulting, like mechanical engineering, or in the area of civil engineering, geomechanics, or automotive industry, but also software development. The second part, and today we'll focus on optiSLang, besides the other products SOS and Multipla. optiSLang is a general purpose tool for variation analysis. That means you can use your CAE-based data to do variation analysis, to do design exploration or data exploration. You can calibrate your virtual model versus real test data. Of course, you can do optimization of your product. You can also quantify the product robustness and the reliability. And putting optimization and robustness together means then to do a robust design optimization and design for Six Sigma. For all these methods, it is necessary to automate your process chain. That means at the moment you're probably working the following way. You have a certain setup, a certain product, you have a geometry, you do the meshing, you do the calculations, and then you double check the results, you do some changes in the geometry, and then go back to meshing and to calculation, check the results again in an iterative way. In order to deduct all these methods, like variation analysis, optimization, we have to automate our process. And optiSLang tries to support you as much as we can with the automation. Here you can see a preview of the optiSLang graphical user interface, where we have different nodes, like text input node, solver node, or text output node, or a workbench node. And with the help of these nodes, you can directly connect to your solver and automate the process you have at the moment. And optiSLang can connect basically to every CAE-based solver, like ANSYS, Excel, CFturbo, and so on. Every solver that has a text input and text output interface and can be called in batch mode can be used in optiSLang. Once this process has been automated, we can use this process chain and go through this all the time with different inputs and getting outputs from the solver. And this is always shown for variation analysis, for optimization in our post-processing. This slide expresses the best practice recommendation for robust design optimization. We always start with the process and automation, which I described before, so to automate your process. The next step is an optional one, do a model calibration. Here we can identify important material model parameters and find a good fit between measurement and simulation. First crucial point in our loop is then the design understanding process, which is our sensitivity analysis. That means that we want to investigate which are the important parameters, reviews, the complexity, reduce the unimportant variables, and generate meta models. And with the help of these meta models, we understand in a better way how our response behaves. And with the help of the information of the sensitivity analysis, we can do the optimization then, either on the generated meta models in order to get fast results if they have a good accuracy, or you can also do direct optimization with real solver calls. Once this optimization has been done, there is always the design quality check to check the quality of the design. That means to put some scattering on the input parameters that you have defined, which occur in real life, like for Young's modulus for a material or for a certain geometry due to manufacturing tolerances. And then we can check how our responses behave if we put such a scattering on the input. And if this is largely unaffected by the scattering response, then we are done. We have a robust design. Or if there is some significant scattering to the input scattering, then we have to do the optimization again with maybe different criteria and go back after the optimization to the robustness again. And if the design is robust now, then you are done. Now let's directly move to the first case study and to the presentation of CFturbo, which is now done by Maya Scofanti, optimization of an axial pump.
Okay. I would like to start with a short introduction into CFturbo. Afterwards, we will have a look at an optimization example by means of an axial pump. CFturbo is a modern, powerful and user-friendly software for conceptual turbomachinery designs. We have about 160 active clients globally, and with CFturbo you are able to design pumps, blowers, compressors, turbines, stators and diffusers, vane and vaneless, and of course volutes. Besides this, CFturbo is offering CRE consulting services like the turbomachinery design or simulation, and furthermore workflows like the following optimization example, for instance. At the beginning of the development process of a new product, you normally have requirements which the product has to fulfill. In our case, the pump should achieve a head of 4.75 meters at the volumetric rate flow of about 1.5 cubic meter per second and at a speed of 780 revolutions per minute. The pump should have the best possible efficiency, and maximizing of the efficiency will be the main objective of our optimization process. Additionally, two constraints have been imposed. The blade angle should be lower than 90 degrees, and the total pressure difference or the total head should be within a range of plus minus 10% of its nominal value. The definition of our design point, we will be guided step by step through the whole or entire design process. First, we have to calculate our main dimensions. This is done by using empirical parameters. Here in this case, the work coefficient and the diameter ratio for hub and shroud. We can design our meridional contour, which is just a pipe or a pipe in our case, but we can define our leading edge and our trailing edge. We have to define our blade angles at the inlet and at the trailing edge. These are calculated automatically due to the use of the free vortex design method. We can define our blade mean lines. And I have to mention that each geometry is described by a Bezier spline, and each control points of this Bezier spline can be used as an optimization parameter. At the end, we get the design of our pump. So, CFturbo provides a fully parametric geometry model of machines, and each parameter can be used for optimization. We used pump links as CFD solver because it is a CFD system with a high solver speed, and therefore it's very suitable for optimization tasks. Even on meshes with a low number of nodes, it has a satisfying accuracy. After the initial geometry has been designed, the optimization parameters has to be chosen. These are in detail the hub and the shroud diameter, the axial extension, and also the position, the axial position of the leading and of the trailing edge. Here we see the reference values, and here the range of variation. Two simplifications have been met. Hub and shroud are axis parallel, and we have just a straight leading and a straight trailing edge. In addition, the number of blades, but also the tangential coordinate of the leading and trailing edge at hub and shroud has been set as parameters too. Furthermore, the 4 control points of the Bezier splines. As I mentioned before, the pump is designed using the 3-vortex design method, and this implies that in each design, the blade angles at the trailing and at the leading edge are calculated automatically. Consequently, the blade angles are not part of the optimization parameters. The optimization cycle is driven by optiSLang, which controls CFturbo and pump links. In detail, optiSLang performs a variation of the geometry parameters. CFturbo makes a geometry update and a geometry export. Meshing and CFD simulation are carried out using our CFD solver pump links. Finally, the results are evaluated and returned to optiSLang. Now the geometry and the optimization cycle has been designed, and the sensitivity analysis can be done for better design understanding. Main goal is to investigate the sensitivities of the parameters. The advanced Latin hypercube sampling was used to scatter the parameters in the design space. 3 analyses with different number of samples have been carried out. In all cases, we can say that about 85% of the samples were graded, 15% failed due to not reasonable geometry parameters, and about 2–3% due to simulation errors. The coefficient of prognosis was improved by increasing the number of the samples, but for the efficiency, the coefficient of prognosis is not as good as for the pressure difference or for the power. This is due to the fact that it is calculated by the other 2 values, pressure difference and power, and consequently it accumulates all answer distance. But the sensitivity analysis identifies that only 7 parameters are important, which are in detail: the shroud diameter, axial extension, the tangential coordinate of the leading and trailing edge, the axial position of the leading and trailing edge, and also the number of blades. So we can say that our set of parameters can be reduced from 15 to only 7 parameters. As an example, the response surface for pressure difference is shown here. The pressure difference rises with higher suction diameter and axial extension. Here we see some geometry examples of the sensitivity analysis. One can see how much the optimizer is varying the geometry. So we have a wide range of variation. The next step in our optimization cycle is to make the optimization itself. Thus, the COP for efficiency was quite low. We decided to perform a direct optimization, but with the reduced number of parameters. For both optimization methods, the EA and the adaptive response surface method, we gain about 5% in efficiency. The EA took about 3 days, the adaptive response surface method about 5 days. So it was a little bit slower to find the optimum. But 5 days are a reasonable time for an optimization. And this was done on a normal desktop PC. The simulation time per sample was about 15 minutes. Finally, a comparison of the initial and the optimized designs. Both optimized designs looks quite similar. In both cases, the position of the leading edge at the shroud moved back. So the optimizer introduced a backward sweep. And in case of the evolutionary algorithm, we see some geometry modifications at the trailing edge. So what we can conclude. The workflow, including CFturbo, pump links, and optiSLang, was successfully set up. CFturbo initial design can be used as a very reasonable starting point. CFturbo provides a well-parameterized geometry that enables to work in a wide range, or a wide parameter range. Pump link solver speed is beneficial for optimization and enables optimization on desktop PCs. By the sensitivity analysis, the important parameters could be identified and reduced to about 50%, and the efficiency could be improved by 5% compared to the reference design. So
now let's have a look at the second case study, performance map analysis of the radial turbo compressor. Again, we'll have a look at the aim of the analysis, the automated workflow, variation analysis, optimization, and the summary. The turbocharger is a good example for a turbo machine that's not only working at one operating point, but on multiple operating points. And of course, if you want to do optimization, you want to optimize all these operating points. They are shown, for example, in a performance map like this, where you see pressure ratio versus corrected mass flow. And the operating points are limited due to surge line, speed line, and choke line. And the first dimension here is efficiency, for example. Now, if we move to optimization, if we want to do optimization and we have a look at one operating point, and maybe we want to increase efficiency at this operating point, we will do some geometry changes, but due to these geometry changes, the other reference points, like the surge line, the choke line, will not be conserved due to the parameter changes. So it will move as well. So let me give an example for that. If we say we want to increase the section diameter or increase height and decrease the back speed, better too, then there's a tendency of having higher choke mass flows. So speedline maybe looks like that. The other way around, if we increase beta 2, decrease the height B2, or decrease the fraction diameter, then there's a tendency of having a lower choke mass flow, like you can see here in red, the red speed line. So the question is now, how can we analyze these performance maps and how can we compare different performance maps if these reference points are not conserved? So this is the question and the aim of this analysis. So now let's have a look at the CAE process. How was this captured in an automated workflow? Here you can see a schematic of this workflow. The first point is always to start with the geometry, which has been done in this case by CFturbo. Then do the meshing. And after the meshing, you need to run the solver all the time for calculating all the operating points of the performance map. And this whole process is then driven by optiSLang. And you can see a screenshot from the optiSLang summary where this workflow has been implemented, and we'd like to go through these different nodes within optiSLang explaining this process chain. At the beginning, there is a geometry generation, which is done by CFturbo, and CFturbo allows geometry variations in a large design space. So this has been done. The next node is then here the meshing. It's done with TurboGrid, and as you can see, we use periodic segments. And the next task is then within these inner systems to calculate the performance map. How is this done? We begin with calculating the choke mass flow. That means with one CFE setup, we are able to calculate the choke mass flow. This is made with the help of dimensional analysis. And this gives us back the choke mass flow of one speed line. So this can be further left or further right in the performance map. And this is the starting point then for doing the operating point within the next inner system. So starting from the found choke point, we constantly reduce the corrected mass flow and calculate one operating point after another. And then you have to stop at a certain point. This can be defined by the user. In this case, it stops when the efficiency drops the first time between two operating points. Then this inner system is done. We can go back to the next speed line. Again, the choke point can be calculated. The information can be handed in to the inner operating system, and all the different operating points can be calculated again. If all speed lines are calculated, there's some data mining, and then the design is done. So once our process has been automated, we can now do the sensitivity analysis. A crucial question in optimization and variation analysis is always parameterization. So let's have a look at the parameters that have been used in this case study. The global parameter D2 has been kept constant. D2 and DS fraction diameter has been changed. Moreover, the leading edge of the main and the splitter blade has been changed. And this is a good example to explain that you can put all the knowledge that you have from your system into the parameterization. So you know that to change the position of the leading edge of the splitter blade on Harper and Stroud independent would not make sense, because designs like these could happen. So you can make dependent parameters. And this is, in order to get designs like this, that always makes sense. And this has been done, for example, for the blade angles as well, beta 1 and beta 2. For example, the beta 2 angle at the shroud is independently varied, but the position on the hub is then dependent from the angle on the shroud plus a certain delta. Moreover, the yield curves of hub and shroud have been used as 12 parameters. The number of blades, the blade mean line, and the rep angle has been a parameter as well. So in total, we have 31 free parameters. Once the process is automated and the parameters are defined, you can start with the sensitivity analysis. Sensitivity analysis evaluates the variance of the input and the output parameter. For example, the output parameter is the pressure ratio, and you get an idea which of the mentioned input parameters influence your pressure ratio the most. So which steps are done in a sensitivity analysis? Basically 3. The first is to define design of experiments within design space, and then calculate all these designs. In our case, one design is not only one solver call, it's the calculation of a whole performance map. So there are multiple operating points within one design. Once everything is calculated, you can use regression models, set up meta models, for example, for one operating point. For example, the maximum pressure ratio of a performance of a speed line, the maximum pressure ratio of a speed line, maximum efficiency of a speed line, and then setting up a meta model for that. And with the help of these meta models, we can evaluate which are the important parameters for these response, for these pressure ratio, for example. Now let's have a look at the results. In this case, the corrected mass flow has been constantly reduced by this value, and a maximum number of operatings per speed line was 6, and the number of speed lines has been 2. In this whole process, 88% of the designs were successful, 1% failed due to in the geometry generation, 5% due to meshing, and 6% within the solver call. So one operating point at choke or speed could not calculate it, or a whole speed line could not evaluate it. These might be reasons for these stages. If we set up response surfaces dependent on multiple input parameters, on multiple geometry parameters, we have to find a good measure for the quality of the response surface, because we don't want to have a good fit, we want to have a good prognosis quality of our response surface. And this is what we get from the COP, the coefficient of prognosis. It tells you how reliable, how good is the prognosis quality of a response surface. In this case, 6 response surveys have been set up in a total completely automated workflow for 2 speed lines, first speed line and the second speed line, and it has been evaluated maximum pressure ratio, maximum efficiency, and the choke mass flow. The COP value is normalized, so between 0 and 100%. 100% would be excellent, 0% would be very bad. So you can see here that choke mass flow and the pressure ratio of the first speed line has some high COP values. The pressure ratio of the second speed line and the efficiencies have a rather low COP value. If you want to increase these values, you have to introduce more designs or reduce these difference here. And so in order to calculate more designs on a speed line, or a third opportunity might be to have a fixed DOE within one performance map analysis. So to have 6 operating points here that you analyze. So now let's have a closer look to the results and the response surfaces. And for that, I'd like to move to the optiSLang post-processing. You can see the optiSLang post-processing. you see the response surface. In this case, for a pressure ratio, you can see the important parameters for this response surface, for this response. Here you can see the residual plot. It's coming from the generation of the response surface itself. And you can see the COP matrix, where we have all our responses in, for example, the corrected mass, the choke mass flows, the pressure ratios, and the efficiencies for both speed lines. Now let's have a look at the results. For example, for the pressure ratio, important parameters are the beta 2 angle at the shroud position and the section diameter. They are mainly driving this, but there are also other parameters that are important. In total, there are 7 parameters indicated as important from 31 in total. So, for example, the number of blades, or beta 1, or the position of the leading edge of the shroud. In total, 11 parameters have been selected to be important from 31 in total. We can also have a look at, for example, the choke mass flow for one speed line, and we can see that the beta 2 angle at the shroud position is mainly driving this, the most important parameter. Sorry. The most important parameter. And we see that with the decreasing of the beta 2 angle, the choke mass flow is increasing, and with an increasing of the section diameter, the choke mass flow is increasing as well. And often it helps also to put in some responses from the solver, to put in some pictures, for example, that you get within the CAE process chain, and to have a look at these pictures in the post-processing. And this is what you can do in the post-processing as well. You can just select the file you want to have. For example, like this, coming from CFturbo, a meridional view. And maybe we can close this one, rearrange it. And then you get a picture from the current design. This might be an interesting design with an high choke mass flow, or maybe this one. And you see in both cases, for example, the section diameter is rather big, compared to maybe designs like this, where you can see a rather low section diameter. And you see that it's automatically connected. So you see the picture of the meridional contour of design 77, and here it's automatically updated to design 117. Okay, now let's move back to the presentation. After we've done sensitivity analysis, we can do the optimization. In this case, the optimization was done on the response surface, and this is very attractive because it's very fast. Also, the COP values are not that high. The advantage is that it's very fast and you can easily change the objective function. So in this case, within the objective function, the maximum choke mass flow, the maximum efficiency of a speed line, and the maximum pressure ratio was put into account. And this for all speed lines. So that means for 2 speed lines in total we have 6 response surfaces, and a global evolutionary algorithm was used for the optimization, and the best design was validated then with a real turbo core calling CFD and CFD analyzer. And as I mentioned, this is done within minutes, the optimization on the response surface, and then you can have a look at the results, change again your objective function, and do the calculation on the response surface again. This has been done, and after that we analyzed the reference design and the optimized design on the MLP in more details. So we calculated more operating points, and we can have a look at the results regarding both speed lines. We can see, for example, the pressure ratio has been increased at both speed lines. The choke mass flow has been increased, and the efficiency keeps constant or slightly decreased compared the reference with the optimized design. Here you can see the performance map of these turbo compressor, where you can see the pressure ratio versus the mass flow, and the third dimension is then here the speed, and the fourth dimension, the bubble size, is the efficiency. And here you can see the initial design compared to the best design, and for better comparison, it's also helpful to have it in one plot. And here you can see, for example, then the black design is the reference design, and the red one is the optimized design, where you may see the higher pressure ratio and the higher choke mass flow as well. And you see that efficiency nearly keeps constant. So now let's summarize it. With the help of optiSLang, an automated workflow that is adaptive could be realized. Adaptive means dependent on the choke mass flow, we can calculate different operating points. Moreover, the sensitivity has been successfully applied for approximately 90% of the design. And we did an optimization on the response surface with validation of resolver calls as well. And this generally improves the method for performance map analysis in 3D CFD. So thank you very much for listening today to our webinar. If you have further questions, you can contact us under support@dynado.com or under support@CFturbo.com if you have questions to optiSLang or to CFturbo, or questions regarding this webinar. If you want to do such analysis, please feel free to contact us also under training@dynado.com or info@CFturbo.com. Please feel free to get in touch with us if you have questions and if you're interested in these design studies. Now we'll stay another some other minutes in the start session in order to answer questions that you can put in the question and answer field of this session. Okay, so now let's see if we have some questions. Okay, one question is whether this material will be distributed. Yes, we will get an email with the PowerPoint and the video of this session as well. Another question is whether the sensitivity analysis is always necessary. Basically, no, you can also do a direct optimization. Of course, it's possible, but the sensitivity analysis has different advantages. So, for example, if you do a direct optimization, you have to define your objective function at the beginning. But often, you don't know how strong the variation is of parts of your objective. So, for example, the efficiency or the pressure ratio. And if the change of the pressure ratio is much bigger than the change in the efficiency, automatically the pressure ratio is weighted higher than the efficiency. That means if you do not know how strong your objective is varying, it's hard to define a good objective function. And if you change the objective function within a direct optimization, you have to run it with the solver again, maybe 100 or 200 designs. And if you do a sensitivity analysis, you first scan your design space. You know about the variation of your responses. You know if your solver or your process chain is creating in a certain design space some errors or some noise because something is not working in your process chain. So this is all these information you gain from the sensitivity, and you find out which are the important parameters. And this helps you to choose a more efficient optimization algorithm later. So, of course, you can do direct optimization, but there are multiple good reasons to start with sensitivity analysis.
Markus, the next question is it possible to, or if CFturbo has an interface to external material database? Yes, we have an interface to CoolProp, and you are able to import each material from CoolProp into CFturbo.
Okay, there is one more question. The question is whether you need both CFD solvers for optimization, Pumplings and CFX, and if other software packages are supported as well, like Fluent or StarCFM+. So, of course, you don't need both solvers. It was just to show you the big variation that is possible. optiSLang can basically work with all different solvers, with Pumplings, with CFX, with Fluent, or with StarCFM+. The interface, the process integration may always look a bit different. For example, for Pumplings, you saw that you can use the text-based interface, or for StarCFM+ as well. For CFX, you can also use the Workbench node, for example, where we directly connect to Workbench project, or you can work with the standalone CFX version. So optiSLang is providing interfaces to all the different CFD solvers.
Okay, next question is if it's possible to optimize multiple components or stages. Of course, it is possible. You can optimize as much components, stages as you want. The entire geometry is parametric, and so you have absolutely no limitations. The only limitation is time.
Okay, there's one more question. Are there other optimization softwares available together with CFturbo? And as far as I know, there are some other software tools for optimization with CFturbo. And on the other side as well, you can use different preprocessor tools for creating a geometry besides CFturbo and use this in optiSLang. So both companies have a good interface, so they work together, and this process is proven, it's in use. That's why we represented this here together as well. But both are also open platforms, so you can use CFturbo together with different CFD solvers and with different optimization algorithms. And of course, you can use in optiSLang also different tools for geometry generation. Then thank you, Miles, for presenting in this webinar. Thank you for listening, and please feel free to contact us if you have any further questions. Thank you and goodbye.
Bye.